Sorry, yeah, thank you. So what is dx by dt?
1.
What is dy by dt?
X.
What is dz by dt?
Square.
What is x of s0? Hmm? Hmm?
S.
What is
S.
what is y of s0?
S square by 2.
Good. What is z of s comma 0?
Yes.
So now what is the Jacobian? Del x by del s, del x by del t, del y by del s, del y by del t at time t equal to 0. So what is this? Del x by del s,
1.
1.
del y by del s,
S.
del x by del t,
1.
del y by del t,
S.
because we have to take time t equal to 0. Del x del y by del t is equal to x, but at the time t equal to 0 it is this one, s. So what is the Jacobian? So this surface is not this curve gamma, or the projection of gamma, the projection, this is we call this curve s comma s square by 2, this curve comma 0, let's say its projection on the xy plane is a characteristic curve. So we cannot directly apply the method, right? You remember? Okay. So we take a modified problem. We consider a modified problem. Consider a modified problem. And we solve it, right? What is that problem? Modified problem. Del x by del t is equal to 1. Del y by del t equal to x. And del z by del t is equal to z. Actually, we are considering the problem, the same problem, ux plus x uy is equal to u square, u0 of y is equal to some different h of y. So we solve this problem, right? And you know how to solve this, and we get that u of xy, you know, it will be h of y minus x square by 2 by 1 minus x h of y minus x square by 2. And we see that when x equal to y equal to x square, we have u of x square that has to be satisfied. That is h0 by 1 minus x h0. Yes or no? And we show that all the solutions. So the solution exists if and only if the initial condition in the initial, this g has to be of this one. Yes, and all other solutions are all, and there will be infinitely many solutions, and the solutions look like c plus f of y minus x square by 2 by the family of solutions, one family, f of y minus x square by 2, such that any f such that f0 is. Okay, so until last class we have done only the semilinear PDEs. Okay, semilinear and the linear PDEs. Now we would like to, so next, as I always say that when we did the Cauchy problem, where we have seen that gives you the existence and uniqueness near locally, not globally, right? But as you've seen in this problem, that in the linear problem or the semilinear problem, we have a global, some of the problem we have a global existence, right? Yes or no? Yes, because in time that ODE
Yes,
has a
sir.
solution for all time or all s. Okay, for all t. Okay, because this is a property of linearity of the ODE or semilinearity. Now let us see what happens for the quasi-linear. Okay, things will be more difficult in quasi-linear PDE. Okay, of course that Cauchy problem, that is a very general theory, and that gives you only a local existence. But as we say that I said that It depends on the problem to problem when you will have a local existence or a global existence. Okay, let's try now give more concentration on quasi-linear equations. Okay, quasi-linear equations. Okay, what type of equation is that? This is a very famous equation. I did now Burger's equation. I said something, right? We start with the Burger's equations. These are called Burgers. So there is a mathematician's name Burger. That is why the equation came. Burger's equation. Burger's equation. Okay, and this is used for modeling. Used these PDE. Just this is a side remark. You can say this is just a physical motivation. We use this type of PDE in studying fluid flow. As I said, right, fluid flows. When the fluid flow, it will be governed by some equation. It will be fluid flows. Okay, the equation look like. Of course, I'm writing in a very reduced form. Ux plus ut is equal to 0, and u of x0 is equal to hx. This type of equation arises in the study of fluid flows. That's the physical context. Okay, and of course, this is one of the very famous equations. Okay, so this is called Burger's equation. This type of equation. So can you tell me what classification you can give to this problem? What type of problem it is?
Quasi-linear.
Why? Because the coefficient of the highest order derivative. What are the highest order derivative here? Ux and ut. These are the highest order. The coefficient of the highest order derivative will have a n. You remember k. Let's say if the highest order is k, then the coefficient can have a term up to k minus 1. And what is the order is 1. So the k minus 1 is 0. 0 order term is the function u itself. So this u is there. Okay, and this is 1, of course. If this is 1, then you know this is not this is a linear PDE, not a it is not also a semi-linear PDE, right? But now we have ux1, so highest order is 1, and with the coefficient of the highest order has a function sitting inside is u. Okay, if it's x only x or x y, then it's a semi-linear PDE. Okay, so now this is a very famous quasi-linear PDE called Burger's equation. Okay, let's try to solve this PDE. The method we have already seen in the characteristic. Now, what are the characteristic equation? Can you tell me? Who will tell me? So let of course let us take gamma. What is the gamma? Capital gamma, the initial parameterized curve. What should be? Huh?
S0 HS.
0 SS.
Very good. What are the characteristic equation? What will be dx by dt?
Z.
Very good. What is dy by dt?
1.
What is dz by dt?
0.
What is the initial condition x s0?
S.
Good. Y s0?
0.
Z s0?
H of S.
Now tell me, what is the solution? From here first you try. Dy by dt equal to 1. So y is some y naught, right? Y equal to y naught, but y at s0 is 0. So what happened? Y equal to t plus some y naught at time t equal to 0. That y naught is equal to 0. So y equal to t is the solution. First, y equal to t. What is z equal to? What will be the solution? This one?
H of S.
Z is h of s. And what is this one?
T into h of s plus s.
X of st is what happened? What should be this? H of s t plus s. Okay. Okay? Is it okay? Yes or no? Yes, sir. Oh.
So in PD we have y.
Ha.
Where in PD we have u times ux plus uy, not ut.
Oh, sorry. Okay. Let us put ui. Okay? Is it okay? Same thing, right? T is a variable, y is a variable. Same thing, right? Am I right? Yeah, it will better to put it y because t is there del x by dt. Thank you very much. Thank you very much. This is a yeah. I should put y. Otherwise, we have if I put t, then we have to change those t, right? Is it clear to all? Why I am putting this? Yes or no?
Yes, sir.
Okay. Okay. So this is. So what is the characteristic line? Yes, I can substitute as h of s, t is y, y of ts of course s. So what is the equation of this? Xt is equal to h of sy plus t. So what is dx by dt? Dx by dy? What is dx by dy? What is dx by dy? Let's put, if we change the variable, let's put, sorry, x equal to, if we change the variable, x equal to y plus, you can put s also. You can change s, but okay, anyway, doesn't matter. What is dx by dy? Hello? What is dx by dy?
H of s.
So this is the equation of a, this is the equation of a, what is the equation of this? This is the equation of a, this is the equation of x equal to, what is the equation of this? What is the equation of this?
Line.
Line. So what is dx by dy? The slope. So what is the slope?
HS.
Yes. Slope or the speed. Speed of the curve. Okay. Is h of s. Now we can invert the variable of now just this is just for your information. The slope is now. Now if I invert the variable t equal to y and s equal to x minus s equal to x minus y zy. Okay, zy. So the solution is, so the solution is u of xy equal, because we know, because we have to invert it, right? Z, that is h of x minus zy. That is h of x minus uy. So u of xy, the solution is h of x minus uy. Okay. Now let us see what is, so this is a solution, you solved it, right? Yes or no? Yes or no?
Yes.
Yes, sir.
Okay.
Yes, sir.
Okay. Now let us concentrate on this line. What is this line? X equal to h of s y plus s. Okay. As we said, the speed, this is called the characteristic lines, right? These are the characteristic lines. Characteristic lines. Okay. Thus dx by dy is x. This is the slope. Okay, or the speed. Let us draw. Let's see what happens. This is of course x ts. This is what. Okay. Let, this is s1, let's say. This is S2 or S2. This is S1, let's say. This is S2. Okay. Let gamma 1 be the characteristic line. Characteristic curve or a line. Of course, here it's a line at S1 with starting speed, with slope, or a starting speed we call starting speed h of S1. So how it will be look like? Anyone, any idea? Let's say from here, this is your line, x equal to h of S1 starting speed, S1 sy sorry sy plus s. Okay, okay. Starting point, the slope is h of S1 because it starts from S1. Okay, and let gamma 2 be the characteristic line. Starting from S1, and you know what is that? Starting from S1 here, characteristic line at S2 with speed h of S2. Let's say speed is S2. This line is x of h of S2 y plus S2. Two line. Okay. Now you can ask me why this intersect. It can happen that it will also go like this. Right? Let us see. Let us assume that if this line intersect, then what happens? If nu1 and nu2 intersects, then what will happen? Then this type of thing happen. S2, S1 like this. Somewhere it intersect, right? Then what is the meaning of intersect at the point of intersection? What is that? S1 plus h of S1 y should be equal to, because this is the equation, x equal to this, h of S1 plus S1, x is equal to h of S2 y plus S2, because it starts from the point S2 with the slope h of S2. Okay, now I say that suppose S1 intersect to S2, that means this 2 x1 should be equal to x2, right? This x should be equal to this. So this is S2 plus h of S2 into y. If we calculate, we will get that y equal to S1 minus S2 by h of S2 minus h of S1. Why? We know already that y equal to t. Yeah. So we obtain that t equal to S1 minus, we know because for this problem we know that t equal to y, S2 by h of S2 minus h of S1. Now where t lies, sorry, you understand where t lies, y is non-negative, right? Y is positive, that means t is also positive. Because we want to solve with this quadrant, right? We want to solve here. You remember y is 0 to infinity. That means we want our domain is here. Okay. Okay. That means y, because y positive means t positive. So this is greater than 0. When it is greater than 0, if y is, if this term is greater than 0, then if and only if we know what we want, we know that we want to solve for y, because our domain is y greater than equal to 0. So if we want y greater than equal to 0, then what should be this one? If and only if what? S1 is greater than S2 and h of S2 should be greater than h of S1. What type of function h is?
Increasing.
Are anyone following, or you just stop following? Tell me. I will repeat again. Please tell me. There is nothing that you are not following. Please tell me. I will repeat again. Huh? Please tell me. You have a look and tell me. I will wait for 2-3 minutes. So this is our problem. Ux plus uy equal to 0. X is r and y is non-negative. U of x is positive. Sorry, ux 0 is h of x. So we want our domain is here. Initial condition is given here. This is the characteristic line, right? Non-characteristic curve. Of course, we have to check. So the initial space curve is s comma 0 comma h of s belongs to r, right? So I have taken dx. So as we did, you know all those things. Then we solve this problem. H of x minus uy. Okay. Now the question is, now we want to study more, concentrate more clearly what is the characteristic line. So these are the equation, y equal to t and x equal to hs plus hst plus s, right? Now let us consider two. So this is s variable, this is t variable. So let's say s1. So what is the characteristic line passing from s1? What is the equation of a straight line whose slope is hs1? So what is that straight line? What is that curve? Nu1 is what is that line? Nu1 with the characteristic line starting at s1 with a slope of h of s1. So this is the equation, right? Am I right?
Yes, sir. H of
Yes,
S1
sir.
into y plus S1.
Is absolutely correct. Same problem. I am saying this from S2 point. Let us start a line whose slope is h of S2 and passing to, and starting from the point S2. So what is the equation of the line? H of S2 y plus S2. Yes or not?
Yes, sir.
Yes. Okay. Now here let us assume that these two type of line, let's say it intersect. Okay. That means if it intersect, then this will happen. S1 plus hs1y is equal to s2 plus hs2y. If this happens, then we are getting that y is equal to s1 minus s2 by h of s2 minus h of s1. Now we know that because for this equation we know that t equal to y. We have solved this. We have solved this y equal to t. So and we are solving what is our domain? Domain is y. We want to solve the PDE for y positive. That means y positive means this has to be positive. This quantity has to be positive. When it can be positive? If and only if S1 is greater than S2 and h of S2 is greater than h of S1. Then that means h has to be, that means h is
Decreasing function.
decreasing, man, decreasing. H is decreasing. Then if h is decreasing, then and your domain, and then at a point y positive, at some point y positive, the characteristic line intersect. Characteristic line intersect. Clear? Is it clear? If suppose we start the problem from here, we start a problem ux xy where h is a decreasing function. Then what happened? Then you are seeing that, then if h is a decreasing function, then what we are seeing? We are seeing that the characteristic gets intersect. So what will happen at the point, at this point of intersection? Huh? What will happen? What will happen? What happened? What will happen?
Sir, h of s would be equal to s.
H of s? No, I am saying that suppose h is decreasing function. Then we have seen that if h is a decreasing function, then this type of thing happens. Then our at y positive at this at this region, this two line has to intersect somewhere. Yes or no? Is agreed? If h is a decreasing function, then it might happen that the characteristic line intersect. Yes. Now my question is, suppose the characteristic line intersect, then what is the solution? Then what will happen to the solution?
The solution along these two curves will be the same at that point.
Yes. So what is the problem? What is the problem? What is the problem here?
So we can find the solution value at this point, intersection point, then it is same also.
What? Tell me again.
You can find the solution value of solution at this point only, then it suffices.
I please repeat.
If you are able to find the value of the solution at this intersecting point, then it is workable for everyone on these lines.
Is the solution exist globally? My first question. For all t it exists. Huh?
Yes, sir.
It exists for all t. Is the solution exist? Is there a problem at the is there any problem in the intersection line? Because what happened? Because suppose you are here, it can have a solution along this line is a different solution, along this line it has a different solution, it intersects. So what will happen? Is the solution exist globally? Huh?
No, sir.
Why? Why?
Maybe slope are equal or which contribute to Jacobian is equal to 0. Maybe here slope are equal and it contribute to Jacobian 0.
No. So you agree that see this type of situation arises first time, right? In a semi-linear or in a linear PD, you haven't seen this type of. We always have a like this, right? Any point you can have, any point you have, any point you have, right? Yes or no? Ever in semi-linear or the two characteristics never intersect, right? Yes or no?
Yes, sir.
So is there any problem?
No, sir.
Huh? So are you able to understand my question? The question is clear?
Sir, if there are lines that parallel to each, means this these both lines, then we are covering the whole plane. So why it's not exist locally then?
The solution does not exist globally because at the if the two lines intersect, how will you define there? You understand? I will give you an example. Just anyway. So let me I will give many examples. So this phenomena when these two characteristic line intersect, when I will give you when the characteristic lines intersects this phenomena is called gradient catastrophe. Okay, so the remark is, I will tell you later, we will give many examples and we will see that what is the problem. If h prime of s is less than 0 at any point, at any point s, then the solution does not exist globally. We will see why. On the other hand, if h prime of s is greater than or equal to 0, then the solution exists globally. Physically, what it says that, physically what is, this is a very interesting thing. I will tell you why. Physically means if the initial velocity, that the initial velocity means h prime of s naught, s, h prime of s. If the initial velocity of the fluid flow, because it's a model of fluid flow form a non-decreasing function of position, non-decreasing, that means h prime of s greater than or equal to 0, then the fluid flows, in a smooth fashion, So you have something, right? So somewhere here you have something. So along this line, the solution is this. But one can come, suppose you start from here, you've reached here, the same value. So one can come from along this line also. You understand the solution? Suppose you want to find the solution at this point, u of xy. So you come here, you have the same line, same characteristic line, right? So you can come from here also. And also you can come from here straight also. You can come down like this, or you can come the same value. So you say that let's come down here. So it has a no uniqueness of solutions. Okay, the solution does not exist globally uniquely. You understand? There is some problem. There is some problem at the point of intersection when the characteristic intersects. You understand? Is it clear? I will give you many examples. Is it clear now? What is happening? Little bit clear?
Yes, sir.
You understand? You can come from here, but you stop here, then you can come along that line also. You can come along other line also. So there is a problem here. Okay. So this is the thing that this says that if the starting velocity is non-decreasing, then this type of phenomena will not happen. Okay. If it has a decreasing type of starting initial velocity, then it might happen that the two characteristic line intersect. That means the the fluid flow is not smooth. There is some vorticity. There is some disturbance here at the point of intersection. Okay. Okay.
There is a fluctuation of solutions at this point.
Exactly. Because you can start, suppose you want to find the solution here. Earlier what we used to do, you just drop along the characteristic line. Yes, but here you come here, then you might problem that the same value. So this is the same character, it intersects. So you can come from here and then start here the solution. And from here again this. So the solution is not well defined near this position. Okay. Okay. And that is the same, is decreasing, then the fluid flow undergoes shock. And if the initial velocity is decreasing, is decreasing function, in position, then the fluid flow undergo a shock, because at that point there might two possibilities, either it can come here, other. So there is a non-smoothness. The function is not smooth here. You can understand, because there is a, like this, the function is, you don't know, like y equal to mod x function, right? Y equal to mod x kind of situation arises here at this point. Okay, so the fluid flow undergo a shock or some discontinuity at that point. We will see with a example, with a particular example that corresponds to collision of shock that correspond to collision of particles. Because of okay, let us do some example, then it will be more clear. Okay. Okay, let us wait. Just tell me, is it okay, or I will repeat again? Please tell me, is it okay, or I repeat again? Please tell me. I will repeat again if you wish. Mahesh, what happened? Mahesh.
It's okay, sir. It's okay.
Atharva.
Yes, sir, it is clear.
Govind, Manish, Minakshi,
It's okay, sir.
Sagar, Shammi, Sushil Gupta. Yes, is it clear? No one respond. Is it clear?
Yes, sir. It's clear.
Yes, sir.
Yes, sir, it's clear.
Okay, let us start with an example. Okay, UUX plus YUY is equal to X. And U at X at 1 is given 2X. Okay, which type of PDE is this? Which type of PDE is Cauchy linear? Yes, because of the presence of U. But here this is no problem because it is a Y. So it's the presence of U, it makes it a quasi-linear PDE. So you start with your solve this problem. And initial parametrization of gamma. What is gamma? Can anyone tell me? What is gamma?
S1
to S.
Good. Okay. What is dx by dt? Good. dy by dt? Y. dz by dt? Very good. X of S0? S. Y at S0? 1. Z of S0? 2S. Okay. What is the Jacobian? Del x by del s, del x by del t, del y by del s, del y by del t. So what is the Jacobian? Huh? What happened? What is del x by del s?
2S.
Y.
Del x by del s. What is del x by del s?
1.
What is del y by del s?
0.
What is del x by del t?
Z.
And what is that at time t
2S.
equal to 0?
2S.
So this given curve is a non-characteristic curve. Okay? Okay. Now what is the solution? What is the dy by dt equal to y? What does it mean? Dy by dt equal to 1. That means y of st is a constant depend on s e to the power t. But it is given that y at s0 is 1. This implies y at st is e to the power t. That is y equal to e to the power t. Okay. Now you can use the sum trick and you will get d dt by x plus z is x plus z. What is the solution? Same thing. This imply x plus z is a constant time, a constant c1 depend on s e to the power t. X at is initial value, z at is 0 is nothing but time t equal to 1. This is x at z0 is 3s. 3s equal to c1 of s. This imply x plus z is 3s e to the power t. Similarly, one could get that. Similar calculation will give you x minus z is equal to minus s e to the power t. Okay. So we have a solution like this. We have a solution x is equal to 3 by 2 s e to the power t minus half s e to the power minus t. What is z? Z is 3 by 2 s e to the power t plus half s e to the power minus. Just compute it. And y equal to e to the power t. If you compute, hence u of xy is 3 by 2 sy plus half s by y. Okay. If you compute, you will get that this will be s by 2. You can take s by 2 common, 3y plus 1 by y. You know what is y. Okay, because we want everything in y. So, and what is s? S you can compute like that. X equal to s by 2 3y minus 1 by y from here. Okay, because e to the power t is y, you can put e to the power t, and this here you can put, then you have this. Then what we get, s is equal to 2x by here, 2x by 3y minus 1 by y. So if you put here, you will get that x into 3y square plus 1, because you just put the value of s here, by 3y square minus 1. Hence we have a solution u of xy is x into 3y square plus 1 by 3y square minus 1. Now you tell me, is the solution exist globally?
No, sir.
Why? What is the problem?
The denominator part.
Exactly. See, that means this characteristic curve somewhere is getting a intersection. Of course, this is not a straight line, so you could not able to compute it exactly, right? You understand? Because y is e to the power, it's a log y kind of function. That means if some two value, somewhere in the characteristic curve intersect. You understand? That is the reason we are not getting a solution for all x. Clear? Of course, we cannot explicitly see where it is, but this is somewhere it is intersecting, because this is not a straight line now. Okay, somewhere intersect means the solution is does not exist for all. Is it clear? Is it clear? Clear to all?
Yes.
Okay, good. Okay. Sorry. Now let us consider an example of a where the initial condition is only a continuous function. Initial condition is only a continuous function. That means like this. Example. Uy plus ux equal to 0. X belongs to R. Y positive. u of x0 is equal to h of x. And what is h of x? 1 if x is negative. It is 1 minus x if x between 0 to 1. Okay, and 0 if x is greater. How the graph look like of h? Earlier it is x equal to 2x, 0, like that, right? S square by 2 all on. Now we have something different one. So the function h looks like this. This 1 minus is a straight line here, and here is 0. This is 1, this is 0. This is x less than 0, this is x greater than 1. So this is the function. So of course this is a continuous, just a continuous, not a C1 or anything. This is a continuous function. Okay. Of course, if you take the derivative, there is a problem. So it's a continuous function, just a continuous function, not a C1 function. Please see that, not a C1 function. Okay. Now let us solve this problem. Okay. Clear? Is the question clear? All of you? Is the question clear to all of you?
Yes, sir.
Okay. Now let us see how the solution look like, and you will see that what happens to the characteristics. Okay. So the initial parametrized space curve gamma is S0 h of s. Of course, now the h of s is it is a problematic. We will see. S belongs to R. Okay. What is del x by del t? You tell me. What is del x by del t? What is del x by del t?
Z.
Very good. What is del y by del t?
1.
1. Very good. What is del z by del t?
0.
What happened?
0, sir. 0.
0.
What is xs comma 0?
S.
Ys comma 0?
0.
Zs comma 0?
H of S.
Jacobian? Del x by del s?
1.
Del x by del t?
H of S.
Del y by del s?
0.
Del y by del t?
1.
So it will have certainly a local existence, right? Okay. Now solve this ODE. So what is y of st? So your initial hs is given to be a decreasing function, right? Yes or no? Non-increasing function. Yes or no?
Yes.
Okay. Yst equal to t. What is z? Z equal to h of s. And what is xst? What is x of st? Tell me.
H of S. T plus S.
S plus? Clear? Clear or not? Clear or not?
Yes, sir. Okay.
Yes, sir.
Because just to solve it. Z your h, Z is your h now. Del x by del t h of h of s t plus some s because of this. Okay. Now let us look. X of st you have now s plus th of s. Now how the h of s, now how it looks like? S plus, what is hs? You just tell me. What is HS when S is less than 0? What is that? HS is when S is less than equal to 0. What is HS?
1.
1. Very good. S plus T into 1 minus S when S is between 0 to 1. Okay, and S when, because 0, S is greater than equal to 1. Okay. So what is the slope? Your X is now, your T is Y. T is Y of ST. So X is equal to S plus Y of HS. So what is del X by del Y? Del X by del Y is H of S. H of S is 1. The slope is 1 if S is less than equal to 0. 1 minus S if S is between 0 to 1, and 0 if S is greater than 1. Agreed? You agreed or not?
Yes, sir.
You agreed. So this, of course, this is again a straight line. When S is equal to less than equal to 0, this is your, let's say S, this is your T, this part. This is S greater than 0. When S is less than equal to 0, what is the straight line with a slope 1? How it looks like? Any straight line? What happened? Up to this. Agreed? All of you? This is a straight line. This is a straight line with slope 1. Just a minute. Hello? हाँ, मैं अब थोड़ा बाद में, मैं मीटिंग में हूँ, मैं बाद में. हाँ, anyway, this is the straight line whose slope is 1 for S less than 0. You agreed or not?
Yes, sir.
Agreed. What happened for this is 1? What is the straight line HS equal to 0 for S greater than equal to 1? How the straight line looks like? Slope 0. That means slope is 0. That means
Parallel to S.
Parallel to S.
Parallel to T, man. Agreed? This is T, this is S. Agreed? Agreed or not? If I am doing mistake? Any mistake I am doing? Please tell me. Hello? Is it okay or not? What happened? Yes or no? Something you tell me, man. What happened? Hello, what happened? What happened? Is there any mistake I have done?
No, sir.
Huh?
Fine.
Yeah, Yash, tell me, what is the problem? Mahesh?
No, sir, it's fine.
No, it's
Fine.
not fine. There is some mistake. Y equal, I said S equal to, this is H of S, speed is 0. What does it mean? There is some problem. Why it is a parallel perpendicular to S axis? Why? What happened?
Because the slope is 0.
Slope is 0 means? That means tan 90 degree. What is the tan 90?
Infinity.
Then why I'm drawing like this?
Because we are taking slope like in the reverse order, right? We are looking at slope from the point of view of x-axis and into the y-axis from the beginning.
Here, see, here. We just put our equation is y equal to mx plus c. Instead of we have write x equal to my plus c. Understand? Very good. Very good. That is why.
From the beginning, we are doing this thing, right? Like we are looking from the point of view of x-axis.
Exactly. Very good. Very good. So this happens. Now what happens between 0 to 1? It looks like this. Some here, as it is going, it is like this, right? Like this. Between this 0 to 1, this is 0 to 1. This is like this. This is like this. Agreed? Okay. Now what is this intersection point? So there is a problem here only. Okay? So now for y less than 1, let us say y less than 1, you fixed your y, you invert the variables. Okay? Invert the, you will see there is a problem. What is the variable? Earlier we have x of st is equal to s plus t when s is less than equal to 0, right? S plus t into 1 minus s when s is between 0 to 1, and s when s is greater than equal to 1. Now we want to invert the variable s. S is equal, we know that t equal to y. So if you invert s equal to x minus y, if s is less than 0, that means x minus y is less than y, and x minus y by 1 minus y if y is less than equal to x and x is less than 1. This is all solution I am seeing only for y strictly less than 1 and x when x is greater than equal to, because here s equal to, I am inverting the variable. Okay, I am inverting the variable x minus y. This is s. Now the solution is so the solution for y less than 1 is, I have inverted the variable for y less than 1. So the solution xy equal to h of s. We have seen z equal to h of s. So s is 1. This is 1 because h of s we know that 1 if x is less than y less than 1. 1 minus x. 1 minus x. Now 1 minus x is 1 minus x minus y h of s, right? H of s is 1 minus y minus y, and this is x. Y less than x less than 1, and this is x greater than equal to 1. This is your solution for y less than 1. Now what happens at y equal to 1? What will happen? At u x y equal to 1, this is 1. Y is 1. 1 if x is less than 1. If y equal to 1, then what happened to this function? This is 0 if x is greater. Okay, so this is a discontinuous at x equal to 1. So at y equal to, along that, so singularity is along this line. Along this line y equal to 1, if you see the equation, the solution is u of x1 is 1 0. It can't be. This is not even a continuous. The solution is not continuous. Okay, you understand? But for y less than 1, you have a solution. But at y equal to 1, that means this has a problem. This solution has a discontinuity. You understand? the solution has a discontinuity. The solution is not even continuous. Okay, you understand? Okay. So there is some problem. Your initial HS, the initial curve HS is given to be just a continuous function, but since it's a quasi-linear PDE, you are getting a solution U. At some point they have developed a discontinuity. The solution is not smooth. You understand? The solution is not smooth. So you have only a smooth solution locally. That means you have a solution locally. So you take any point around that, around this, there is around this neighborhood. This is your characteristic curve. Around that neighborhood, y less than 1, you have a smooth solution. You understand? Okay. This is very, very important to understand. I'm waiting here for 2-3 minutes. Please tell me, is there any problem? Then I will move forward. I will repeat again if you wish. That ODE has no smooth continuous solution beyond y greater than equal to 1. There is a problem because this line intersect here. Is it okay? Tell me. I will repeat again if you wish. If anyone has any problem, I will repeat again. There is no shame in asking. You can ask me 1,000 times. I will tell you 1,000 times. So please tell me. May I move forward, or you want me to tell you again this part? This is the phenomena which we were started with in the problem, that if H is a non-decreasing, then it might have a problem. Is that okay to all of you? May
Yes,
I
sir.
forward? Sanjeev, Meenakshi, Yash, Mahesh, Ekansh.
Yes, sir.
Clear?
Yes, sir.
Navneet, Manish, Vishwa Prakash, Deepak.
Yes, sir.
Clear? You understand what happens? Can anyone explain me what happened? So this is very important to understand. This is the most important part in the first order PDE. People always believe that it might have always a continuous solution. No, smooth solution. No, it is not possible to have a smooth solution always. Locally you could have, but not globally. You understand? Tell me, who will explain me? Yash, can you explain me?
Yes, sir.
Yeah, tell me.
But if we take a function has to be not continuous anyway.
I have taken a continuous function H.
Okay, it's continuous, but it's not
C1.
differentiable.
Not
Yes,
C1.
yes.
Yeah. Then what happened?
So we find out the solution and we see that there are some points where there is means points of intersection.
Not the solution intersect, the characteristic intersects, right?
Yes, the curves.
Now you have to see that at the point of intersection, there is some problem with the solution, right? At those points. As I explained pictorially, that it might happen that you start from some point, you reach at the point of intersection, then there are two possibilities. You can follow, you can follow one character, either the left hand, the straight way you can follow, or you can have you can follow either of the two characteristics, right? So a continue or not even a continuous, right? Yes, you understand? All of you understand, Mahesh?
So in fact, at y equal 1 or y equal y greater than 1, then we have
Yes.
means our solution does not exist at many
Yes.
points.
Exactly. Yeah, exactly. So for a quasi-linear PDE, you have a really the solution exists locally. So it is very important. We can see that it is indeed the solution exists locally, not globally. Okay. Okay. Now we do just as you mentioned now that you are now I am taking H to be a continuous function, not C1. Now I will like to take that H is only also a discontinuous function. Okay. Now I would like to consider H2 is not continuous. Then what happens? Then you will see that the problem is even worst. The situation is even worst. Okay.
Sir.
Ah.
Sir, for y equal to 1 or y greater than 1, we found u. So u is a weak solution.
What? I haven't talked about weak solution, right?
Oh, no, sir, you told in the first lecture.
No, they exactly. You will see. Yeah, yes, they are something called yes, weak solution. We will see. Yes, yes, very good. So the classical solution does not exist, but some kind of solution might exist. Okay, we'll go there. Very good. We'll go there. Okay. Point-wise sense, classical solution does not exist because you see that it's not a C1. The solution means what we, if we say the classical solution is a C1 solution. That's for clear that the C1 solution does not exist. But that does not mean that because this is one of the most interesting PDE, one of the most interesting PDE people studied. So how then what happens? Then the point is something called physically relevant solution, some physics is there. Of course, we will do mathematically. That something called weak solution will be defined, and we will see that how we can study this PDE without having a solution having a structure C1. Okay, we'll see later all those things. Okay. Now this is something called propagation of discontinuity, but we don't call it. This is something called propagation. So the given H function is discontinuous. Then what happens to the solution? This is something called propagation of discontinuity. Okay. There are some physical situation where the initial condition has discontinuity. That the function h. In this case, we cannot expect the solution to be a classical one. Or something called C1. Okay. One such problem, just we take a particular example. Such problem is called Riemann problem. What is the Riemann problem? The problem of this type. Consider the problem ux plus uy equal to 0, x is in R, y positive, and u of x0 is h of x, just a simple discontinuous function. X is this 0 when x is positive. The function is like this. When x is 0, x is positive. Okay? This h is now a discontinuous function. So what happened to the, can we solve this? Okay. Okay. Immediately tell me what is the equation of a characteristic line? Huh? x of st, just now we have done, right? X of st is equal to y h of s plus s. Agreed or not? Agreed or not? This is nothing but y plus s when s negative and s when s positive. What is the speed? Del x by del y is, huh? What is del x by del y? H. Okay, so the speed is 1 and 0 if s is positive. Sorry, if s is negative, this is 1, and s is positive, the speed is 0. Slope is infinity. Speed is 0. So what happened? So what looks like? How the characteristic lines looks like? How characteristic line look like? How characteristic lines look like? Huh? What happened? So the line is x of st is y of st h of s plus s. So the speed is del x by del y is h of s. This is 1 if s is less than 0. This is 0 when s is positive. So this is a straight line. So this is the when s is less than 0. This is 0. This is s is positive. And when s is greater than 0, this is 0. So what happened? So the characteristic line intersect for all s positive. For all s positive, it intersects because you understand it intersects. Okay. So then how to solve this problem? Okay. Now, but just look. Instead of this discontinuity 1 0, if I given 0 1, then what happened? Can anyone tell me what happened then? Suppose I have given this h of x is given to be 0 if x is less than 0, 1 if x is greater than 0. What happened? Then x of ts is equal to y of ts h of s plus s. Right? Huh? Right? Then if you draw the picture, then this is s and this is y plus s. S less than 0 and s plus. The pictures look like then s positive. S positive again, it's a straight line with slope 1. And s is straight line like this. There is no intersection. Okay, there is no intersection. But what if we take this type of discontinuity? It has an intersection. Then how to define? Because here not even locally it is, because h is now discontinuous. We cannot, because the initial conditions for a C1 solution we need for the existence and uniqueness of ODE. You remember A, B, C, the coefficient A, B, C and H are C1 function. Now this is not a, or at least it is a and the initial, sorry, they are C1 and the initial function is a continuous function. Now HS is a discontinuous function. Then for S positive you have no solution. For not even locally, you don't have a solution locally also, because it has a, this is your characteristic line, right? If you see locally, the intersection is there. Not even have a local solution. It does not contradict any existence or uniqueness of Picard's theorem, because the initial condition here is not given to be continuous. It is a discontinuous function, initial condition. Okay. So the characteristic intersects for any S positive. Then the question is how to define a concept of solution here. Concept of solution in this case. In this case. Okay. And similarly, the same question we can ask how to say here again the same thing. How to here, of course, we can define the classical one, but something more. How to define a new kind of concept, a new concept of solution, in which includes both the case, which includes both the case, both the cases. That means when S is this type of function, you should have some when is S is 1, 0 or 0, 1. Okay, some kind, because here the solution does not exist even locally. But of course, this does not contradicts the Picard's theorem. Okay. Okay. You understand the point? So because for every S it has a intersection. Okay. Okay.
Or in the next page.
Yes. Here along this line you have a solution. If S is less than 0, then you have a solution. You understand? You have a solution for
in
S
the
less
next
than
diagram, why we don't have solution. In this diagram.
Yeah, in this class, what is you are saying?
The curves are not intersecting any.
Yeah, then you have a solution. Here you have a solution.
Yes.
Of course, you have a solution. But I want to say that this is something, right? I have to say some when is H is 0, 1, you have a solution. But H is 1, 0, you don't have a solution. This does not sounds good, right? You should have a uniform meaning of a concept of solution, which includes both the cases. You understand?
And so why we are not defining H at point 0?
When?
At point S equal to 0.
Which point? I did not understand. Please. No. It is S greater.
Okay.
Sorry, this is not an issue. Sorry. This is okay. So for S less than 0, you have a solution. But when S greater than 0, you don't have a solution because it is intersect. You understand? For S so local again for S less than 0, you have a solution. Okay? Is it okay?
Yes.
Yes, sir.
Yes, sir.
Because any solution here in this quadrant, you have a solution. You can come here. You can. So something is more. So you have to include more thing in the concept of solution. Just C1 solution will not help you, right? Just because like you see. So just like you see here, this type of 1, 0 you have a discontinuity at some point. So you have to build your concept of solution even bigger so that you can include all these concepts. When if it is intersect also, you can somehow define some concept of solution. So this will be we will see in the later class that in the subsequent classes that how to define this type of solutions. Anyway, so this is the problem. This is all for the quasi-linear PDE. From next class, I will do the non-linear PDE, fully non-linear, and finally we will see how to define the concept of solution in this type of situations. Okay, that is all. Then we will move something. That is the syllabus for the first order PDE. 3 more class, 2 or 3 class, 2 or 3. I think 3 class will be needed to finish this first order PDE. Okay. Tell me anything else you want to ask me. Is that clear?
Sir.
Yes.
So what happens if we have linear or a semi-linear PDE and H to be discontinuous?
Yes. You take the same problem and find and define H to be this. What happened? You see. Okay.
Okay, sir.
You take H to be the even continuous case 1 minus X. Instead of you take Ux plus Uy equal to 0. Please tell me in the next class what is happening there. Okay, then only you will understand. Okay. Clear?
Okay, sir. Yes.
You will tell me what happens. It's a very good question. This is the way you should. In this way you can learn things. Is it clear? The thing.
Yes.
So this is a problem. So not even if we define the initial curve for S equal to R, then also for just we have a, if you define the initial curve for s less than 0, then you have a solution. If you define s for r, then you don't have a solution. So this is something very interesting, this type of thing, that this continuity appears in the solution automatically. Okay. Anyway, okay, that's all. Okay. Anything you wish to ask me? Would you like to ask me anything, or is it clear? Are you feeling now comfortable in the first order PDE? Yes? Are you feeling comfortable? Anyway, ठीक है. Okay. Okay, bye. Thank you.